All right, we're going to look at a microphone now. And so again, I will not make you, it's not my intention to make you have to do this on exams, uh, but it's interesting to look at. So how does the microphone work in a general sense? Basically, you have a coil in here, so this acts as a generator, generates a voltage, and the current comes out, okay? And then we have a voltage drop, and here's our output, and then there's an inductor in here. Uh, and so there'd be another voltage drop, then it comes back for more input. So what we have then is you have this essentially a plate here, and this is modern microphones use piezoelectric crystals, and so you squeeze the crystal and that creates currents and stuff. This is an old-fashioned type. Okay, so this is different. Um, but so here we have this plate, and of course you have pressure, sound waves, and over the plate that would create a force. So you have a pressure, newtons per meter squared over this area. That creates a force, which causes this plate to move. Uh, it has a spring and damper to kind of regulate its motion, and then that, as it moves back due to pressure against this thing, uh, then you have this coil that goes like this all the way around, coming around. Okay. And that's going to go in and out, in and out, in and out, in and out. Okay. And the whole thing just moves as a, like so. And as that moves in and out, that's moving these conductors within the field, the magnetic field, and that creates the voltage, and the voltage, and then this current runs through, and everything happens. Okay, so the magnetic field goes north to south, north to south. So what you have here is you've got a magnet that is you have the center is the south, and then you have this concentric north running all the way around. Okay, so we have that. So we need to start looking at how we're going to model this thing. Okay, and so what we have here just shows the magnetic field. So you have all of these conductors running around like so. So that's what this is. And then here's south, here's north, and then you have all these wires going in a circular pattern. And so here I'm showing current going like so. And you can see that I'm looking at it this way, which is what that is. And notice what we have here. This is the head of an arrow. These are the tail feathers. So the current's coming out and going in. Oops, sorry. So out, in. So that's what this is showing. Here's the current. Here's the magnetic field going north to south. This is this right here, from there to there. That's the relative to the center. That's the radius of the coil. All right. Now, let's figure out how the forces, what's happening here. Let's just look at this picture first. All right. This is, you apply a pressure because you talk at the microphone. The pressure over a plate creates a force, so I'm calling that force applied. Spring, damper to regulate this thing. That makes complete sense. Now you notice I have Fe. This is the force that's generated because when you push this thing through the field, basically what's going to happen is the field isn't going to appreciate this. And so as you push this through and create a current, a force is going to come back against this plate saying, no, 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 don't like this. How do you see that? Okay, this is Fe, here's Fe. This is the computation of it, but let's just deal with this. Length of conductor in the field. Okay, so you have all these, think of windings, piles and piles and piles and piles of windings every time, or number of turns. So the amount of copper in the field will be 2 pi r, that's the circumference, and then the number of windings or turns, 2 pi rn. So that's what I have there. And then it's I, L cross B. So there you have it, I, L, B. But what about the LB? Okay, so current basically is coming in and going in through the tail feather and around and around and around and at the end it works its way out and comes out this way. Okay, so we have the conductor here. Let's just look at it this way. Here's the conductor in the direction of the current, right, like so, and here's B. So we go L cross B. L, if I look right here, it would be L going across B. Fingers coming out, my thumb, right hand rule, coming out here. So the force, this is a resistive force, all right? And that it's good it works that way, because if it wasn't, just imagine you apply a little force here and you start this thing, and that would push you in all the way farther. Okay, and that would tend to want to make it produce more current. The process of pushing this in produces a current. So it's going to object. All right, that's what we have there. Okay, so we have the current running like so through here. All right, and that's going to create a voltage. So what happens is you move this, that creates a voltage from here to there. Okay, then you have this resistance and stuff, and wham, the current goes out. Okay, so that's how that happens. That's what we're showing here. So here's the output voltage, here's the inductor, which put an L in there. Okay, and then this is basically a generator. So the voltage gets driven up by the force applied here. Well, this is a force applied here, that is, and that creates the current that goes around. So we can handle that as well. Okay, just checking I have everything. Now notice here here's the back voltage. It's the velocity of the conductor cross the magnetic flux times the length of conductor. Okay, we already know how to do the length of conductor, but let's look at the velocity cross B. Okay, so the velocity, you push against this, the velocity is going in here. Okay, and now we have, here's B's going across this way. So we need to make V, right hand rule, cross B, my thumb is going into the paper. So that's what that's saying is that the current is being driven into here, out here. Okay, where the current's being driven, that means that's where you're having this increase in voltage going up. Okay, or as we showed right here. Okay, so V, B, let's go back to this for just a second. These are perpendicular, so with the right-hand rule, that just becomes velocity times the flux density times the conductor length. Okay, so here we have everything's aligned up, current's running this way, the voltage will increase as it goes through, and so we have V, so I'm calling that X dot, B, that's what it is, L, well we just did that, 2 pi R N. All right, so that's the voltage that's driving this thing, and then it goes through a resistor and an inductor, so this voltage will equal R times I plus L di dt. Okay, so there's that piece. And then so now we have the mechanical piece, which we had looked at here. There's a force applied, Fa. There's a damper and a spring related to this plate to keep it from going too wild, I guess. So you have a damper minus X dot minus Kx. And then you have Fe, which we computed up here, I 2 pi Rn, that's L times B. All right. So now we want to convert all this into Laplace. So we have, here's, make sure I have the right equation, right here. We're starting at equation 1, and we're going to take that to Laplace. So the x becomes Sx of x. Derivative is an s. And then all of these are constants, so bam, they're there. Equals R, I of s, Ls, we're using impedance, I of s. So now we can solve for x of s. How far this thing moves is bringing I on the other side. So we have R plus L of s, if we factor out the I of s, divided by all this other stuff. B 2 pi Rn s, and I'm going to call that transfer function 1. So I don't have to keep writing all this stuff over again and it gets messy. So transfer function 1 times I of s would give me x. All right. Now I have my second equation. So here we have, I'll bring all the x stuff to the other side. All right. And so I have now ms squared plus bs plus k, that'll be x of s coming out of here. I bring the bs plus the kx. So, but x of s is equal to t1 times I. So I'll put that in there for the x. And then I have plus 2 pi r nb, and then I have I of s right there, equals the force applied. Okay, so now what I'll do is I'll factor out the I of s, okay, and I'll bring the FA over and bring all of this stuff after I factor it out to the other side. So I have the output current relative to the applied force equals this whole piece. I'll call that transfer function 2 so I don't have to keep on writing it over. Okay, well, if I knew the current and I multiplied by R, I'd have the output voltage. That's what I want. So EO is R times the current, but the current is nothing more than this transfer function, T2, times FA. Bring it back up. All right, and then I can bring FA back down, and I'm left with, here's my final answer, R times transfer function 2, which is this, is the relationship between the output voltage and the input force. And there we have it. Next we're going to do a galvanometer. See you in a moment.